Evening, you guys. You can probably hear some Elvis going in the background. Kieran, our 6-year-old, is doing some dancing with a lightsaber to Elvis. Yep, that's classic. So here we go. This problem, in class we couldn't figure out what the situation was. I finally went through and tackled the physics of it. I was like, what is the deal with this pressure? Well, the pressure on the side, this is pretty mind-boggling. I love these counterintuitive physics principles. Like the idea that the pressure on the side of this container, it is like laying on its side. So it's like a log, like a half of a Twinkie, or actually it's like an upside-down Twinkie. If we lay it on its side, and the pressure on the end cap is what we're trying to find. And it turns out, the amount of water behind that is irrelevant. It's the depth of the water, or the substance, oil in this case, that builds up the pressure. So anyway, so let's take a look at this. So we knew it was 57 pounds per cubic foot for that oil. And it's all about why. How deep it is in that tank is all that matters about pressure. So I put it in yellow there to emphasize it. So what we're going to do, though, for the integral, we're integrating our bands, those blue bands, these blue little strips. We're going to find the area of those. That's the area, the pressure that we're going to calculate. So the area of that one is 2x times delta y, as you can see, and that's trying to show you the strip in the actual tank itself. That's the face, strips of the face of that tank. And that is, sorry, a little pause there, but area is 2x times delta y of that strip, and we're just going to integrate an infinite number of those. And the variable piece, that 2x, I hope you know what I mean by x. X is the width, or half a width of one of those strips, because if you go up to the very top drawing there, x should be the distance from the origin onto the right. The width of any of these would be 2 times x, because it's symmetrical. There's two sides to that. So I put a little drawing here to show you x. Well, anyway, we're going to do this whole delta y, the depth or the width of one of those strips. As soon as we see delta y in there, we're going, we're integrating with respect to y. So any of our functions have to be in terms of y. And so x there can't be in our function. We have to solve for x and get that actually in terms of y. So this next step is, there you are, there's x equals the square root of 11 squared minus y squared. And that's going to be our x term that we'll substitute back into that area function up above. So here it is, looks like that. So there's our area piece. Now that's one component of the whole thing. Now remember, pressure times that area will give you the area where the pressure on that whole fascia, that whole piece, end cap, this vertical end cap that I still think is an ambiguous term, vertical end cap, but I think we get the idea now. So pressure times area, there's our pressure we got earlier on, 57 times y, the depth, so 57 pounds per cubic foot times y, number of feet, and we get square feet of pressure, and then take it times area, which is in square feet again, so we end up with 57y times that lovely formula we got up above in blue. And what we'll do is, that's the band pressure along that band. So that's pressure on each one of those blue bands. Well, we're going to do a whole bunch of those, an infinite number of them from bottom to top of that tank. And when that happens, then we're talking integral. I simplified a little bit. If you notice, the 57 times 2 in our pressure times area made it 114y, and did some little things along the way. But now that we know that's our big pressure of a band, we're going to add up all the bands all the way up from 0 to 11. Here's the integral. There's that 114. I pulled it out front. And this gives us the area, or that pressure along that front fascia. 50,578 pounds of pressure on there, which is no small amount. So my question to you is, so what if we made a tank that, held 10 gallons with that front fascia versus a longer tank that held, 100 gallons with that front fascia? Does that mean that the pressure on that plate is the same regardless of how much water is in there? That's a question I'd love for you to answer for me. All right, hope that helps, and that will also help with the next problem too, which has a triangular front fascia piece. The only thing that's different is how we calculate x. So if you guys go down here, when we got x, because it was a half circle, that's how we got it before. Well, the x you get in the next problem is you're dealing with this triangle, and x would be, of course, that distance across, right there. And you have to calculate that in a different way. It's going to have to do with either similar triangles, overlapping similar triangles, maybe a little Pythagorean theorem. But I'm thinking if you do maybe some similar triangle features, like maybe a height times a width equal to some other height times width. That ought to get you through that. Email with questions.